In the grand story of science, some of its greatest heroes come from the most unexpected places. Consider this. One of the most brilliant minds to ever unravel the universe's secrets was born into a world with very few advantages. Michael Faraday entered the world on September 22, 1791, in a modest part of London. He was the son of a blacksmith, a family that worked hard but struggled with poverty. Young Michael received only the most basic education, just enough to read, write, and do a little bit of math. In a time when great scientists were often gentlemen of wealth and formal university training, Faraday's path seemed destined for a life of manual labor, far from the hallowed halls of scientific discovery. But the universe has a funny way of finding its champions. Even without a classroom, Faraday's mind was a sponge, eager to soak up any knowledge it could find. His world was not one of tutors and textbooks, but of observation and deep, persistent curiosity. He looked at the world around him not just as it was, but as a collection of fascinating puzzles waiting to be solved. How did things work? Why did they behave the way they did? These were the questions that buzzed in his young mind, questions that a formal school might have helped answer, but their absence only made his desire to learn for himself that much stronger. His circumstances were a barrier, but his spirit was relentless. The lack of formal education could have easily extinguished the spark of curiosity in anyone else. For Faraday, however, it became the very fuel for his intellectual fire. He wasn't taught what to think, which left him free to figure out how to think. He developed a habit of questioning everything, of not just accepting facts but seeking to understand the principles behind them. This self-driven education, born from necessity, would later become his greatest asset. It trained him to be a meticulous observer and a creative thinker, unbound by the rigid doctrines that were sometimes taught in the prestigious universities of his day. He was a scientist in the purest sense, even before he knew what that truly meant. This early period of his life is a powerful reminder that genius isn't confined to privileged circles. It can blossom anywhere there is a curious mind and an unyielding will to learn. Faraday's story begins not with accolades and degrees, but with a simple, profound desire to understand the world. His family's humble status and his limited schooling were not the end of his story. They were the unconventional beginning of a journey that would fundamentally change our relationship with the physical world. He started with almost nothing, yet he was about to give the world almost everything, all powered by an invisible force he was destined to reveal. At the age of 14, a pivotal opportunity arose, though it didn't seem like one at the time. To help support his family, Michael Faraday became an apprentice to a local bookbinder and bookseller named George Rebow. For the next 7 years, his job was to bind books, stitching pages together, tooling leather covers, and creating beautiful volumes for others to read. On the surface, it was a manual trade, a respectable but ordinary life path. But for a boy with a thirst for knowledge, being surrounded by books was like being a castaway who had just stumbled upon a freshwater spring. He wasn't just binding pages, he was binding his own future to the world of ideas contained within them. Every book that passed through his hands was a potential teacher. He didn't just bind them, he devoured them. During his breaks and late into the night, he would read voraciously on a wide range of subjects. He was particularly drawn to scientific texts, especially the articles on electricity and chemistry and encyclopedias. One book that profoundly influenced him was Jane Marset's Conversations on Chemistry, which explained complex scientific concepts in a clear and accessible way. He wasn't just reading passively. Faraday took detailed notes, recreated experiments described in the books using simple items like glass vials and wires, and even built his own electrostatic generator. The bookbindery became his university, and the books his professors. This period was more than just an informal education. It was where Faraday developed his signature experimental approach. He learned that knowledge wasn't just something you read about. It was something you tested, verified, and explored with your own hands. He compiled his notes, diagrams, and observations into a meticulously organized, 300-page notebook he called the Philosophical Miscellany. This was not the work of a casual hobbyist. It was the disciplined record-keeping of a budding scientist. He was teaching himself the very essence of the scientific method: observe, question, experiment, and record. His master, Mr. Rebow, recognized his apprentice's unusual passion and, rather than discouraging it, allowed him the time and space to pursue his scientific interests. The 7 years Faraday spent as a bookbinder were the crucible in which his scientific identity was forged. It was here that his raw curiosity was shaped into a focused and systematic pursuit of knowledge. He learned to be patient, precise, and resourceful, skills essential for both bookbinding and experimental science. The world saw a young man learning a trade, but behind the scenes, a scientific giant was taking his first steps. He was building a foundation of knowledge, piece by piece, page by page, that would soon allow him to challenge and expand the very frontiers of science. The bookshop was his launchpad, and he was getting ready for liftoff. Faraday's insatiable curiosity couldn't be contained within the walls of the bookbindery forever. He yearned to be part of the active scientific world he was only reading about. In 1812, a remarkable opportunity presented itself. A customer gave him tickets to attend a series of lectures by the most famous chemist in England, Sir Humphry Davy, at the prestigious Royal Institution. For Faraday, this was like a music lover getting a front-row seat to see the world's greatest composer. He sat in the audience, completely captivated, as Davy demonstrated the wonders of chemistry with flair and expertise. Faraday listened with rapt attention, scribbling down every detail, every experiment, and every idea. It was a glimpse into the world he desperately wanted to join. He didn't just take notes, he turned his lecture notes into a masterpiece. When he returned to the bookbindery, he carefully transcribed, expanded, and illustrated his notes, ultimately creating a beautiful hand-bound volume of over 300 pages. This book was more than just a record of Davy's lectures. It was a testament to Faraday's dedication, his deep understanding of the material, and his skill as a craftsman. But what to do with it? In a bold and life-changing move, Faraday decided to send this magnificent book to Sir Humphry Davy himself, along with a letter explaining his humble background and his passionate desire to leave the world of trade for a life in service of science. It was a long shot, a plea from an unknown apprentice to a scientific superstar. At first, nothing happened. Davy was a busy and important man, and such requests were likely not uncommon. But Faraday's book was different. It was impossible to ignore the sheer quality and dedication evident in its pages. Sometime later, fate intervened. One of Davy's laboratory assistants was fired after a brawl, leaving an unexpected vacancy at the Royal Institution. Remembering the earnest young man and his impressive book of notes, Davy summoned Faraday for an interview. He was impressed by Faraday's intelligence and enthusiasm, but also warned him that a life in science was a harsh mistress, offering little financial reward. Faraday was undeterred. His ambition wasn't for wealth, but for knowledge. In March 1813, Michael Faraday began his new life as a chemical assistant at the Royal Institution. His initial duties were menial cleaning glassware, maintaining the laboratory, and preparing equipment for Davy's experiments. To some, this might have seemed like a step down, but for Faraday, it was the greatest opportunity he could have imagined. He was finally at the heart of the scientific world. He absorbed everything, learning from one of the greatest experimentalists alive. His journey from the bookbindery to the laboratory was complete, all thanks to a daring letter and a beautifully bound book that showcased the brilliance of a mind ready to change the world. Once inside the Royal Institution, Faraday quickly proved he was much more than a mere assistant. His keen mind and deft hands made him an invaluable asset to Sir Humphry Davy, but his own scientific curiosity was burning brighter than ever. In 1820, the scientific world was buzzing with a new discovery by Danish physicist Hans Christian Ørsted, who had shown that an electric current flowing through a wire could deflect a nearby magnetic compass needle. This was the first time a direct link between electricity and magnetism had ever been demonstrated, and it opened up a whole new field of inquiry. Scientists everywhere were trying to understand this mysterious force, but it was Faraday who would take the next giant leap. Faraday pondered the implications of Ørsted's discovery. If an electric current could exert a force on a magnet, could a magnet exert a force on a current-carrying wire? He began to visualize the invisible forces at play, not as simple pushes and pulls in a straight line, but as circular lines of force radiating out from the wire. This was a revolutionary way of thinking. While others were stuck on linear mechanics, Faraday imagined a world of fields and curves. Based on this idea, he devised a brilliant and elegant experiment in 1821 to prove his theory. His goal was to make a wire carrying an electric current move continuously under the influence of a magnet. His setup was ingenious in its simplicity. he placed a bar magnet upright in a pool of mercury, which is a liquid that conducts electricity. He then dangled a wire from a stand above, with its lower tip dipping into the mercury. When he connected a battery, sending an electric current through the wire, something amazing happened. The wire began to spin continuously around the magnet. He had converted electrical energy into continuous mechanical motion. In a second version of the experiment, he fixed the wire and made the magnet rotate around it. This discovery, known as electromagnetic rotation, was the world's first electric motor. It was a simple device, but its implications were monumental. The invention of the electric motor marked Faraday's arrival as a major scientific force in his own right. While the relationship between him and Davy became strained by this independent success, the importance of the discovery was undeniable. Faraday had not just confirmed a connection between electricity and magnetism, he had harnessed it. He had demonstrated a fundamental principle that would become the foundation for countless future technologies. Every device that uses electricity to create motion, from a simple fan to the complex engines powering electric cars and industrial machinery, owes its existence to that humble experiment where a wire first danced around a magnet in a London laboratory. While Faraday is most famous for his work in physics, his contributions to chemistry were equally profound and transformative. Throughout his early years at the Royal Institution, he became a highly skilled analytical chemist, known for his meticulous techniques and sharp observational abilities. He worked on a wide range of projects, from analyzing steel alloys to liquefying gases, a feat previously thought impossible for substances like chlorine. His expertise was so renowned that he was often called upon as an expert witness in legal cases and consulted by industrial companies. It was during one such industrial project in the 1820s that he made a discovery that would open up an entirely new branch of chemistry. At the time, London was illuminated by gas lights, which burned a fuel produced by heating whale oil. This process left behind a sludgy, oily residue that was considered a useless byproduct. Faraday was asked to analyze this residue to better understand its properties. With his characteristic patience and precision, he began the painstaking process of distilling and separating the complex mixture. In 1825, through careful fractional distillation, he isolated a clear, sweet-smelling liquid. He then subjected this mysterious substance to rigorous analysis, determining its elemental composition. It was made of equal parts carbon and hydrogen. He had discovered a new compound which he named bicarborate of hydrogen. At the time, the full significance of this discovery was not immediately apparent. The structure of molecules was still a great mystery, and the world of organic chemistry, the chemistry of carbon-based compounds, was in its infancy. Faraday had identified a new building block of matter, but its true importance would only be realized decades later. The German chemist August Kekulé would eventually deduce the compound's revolutionary ring-like structure and rename it benzene. This breakthrough unlocked the door to understanding a vast family of related compounds, known today as aromatic compounds, which are fundamental to both nature and industry. The discovery of benzene was a cornerstone for the development of modern organic chemistry. It became the parent compound for countless synthetic materials, including dyes, plastics, detergents, pesticides, and pharmaceuticals. The aniline dyes derived from benzene transformed the textile industry, creating vibrant colors that were previously unobtainable. Aspirin, a derivative of a related compound, revolutionized medicine. All of these innovations trace their lineage back to Faraday's patient investigation of a foul-smelling industrial waste product. His work demonstrated that even in the most unpromising materials, hidden scientific treasures could be found by a curious mind with the skill to look for them. Despite his early success with the electric motor, a nagging question remained in Faraday's mind for nearly a decade. He had shown that electricity could produce magnetism and motion, but could the reverse be true? Could magnetism produce electricity? It seemed logical, a beautiful symmetry in the laws of nature, but proving it was incredibly difficult. For years, he and other scientists tried and failed. They would place a magnet next to a wire, expecting a current to appear, but nothing happened. The secret, it turned out, was not in the presence of the magnet, but in its motion. The universe was waiting for someone to see the importance of change. On August 29, 1831, Faraday finally cracked the code. His breakthrough came from an experiment involving an iron ring. He wrapped two separate insulated coils of wire around opposite sides of the ring. He connected one coil to a battery and the other to a galvanometer, an instrument that can detect tiny electric currents. His hypothesis was that the magnetic field created by the first coil would travel through the iron ring and induce a current in the second coil. When he connected the battery, he saw a momentary flicker on the galvanometer, but then the needle returned to zero. The real surprise came when he disconnected the battery. The needle flickered again, but in the opposite direction. Faraday realized the profound truth in that fleeting moment. A steady magnetic field did nothing. The electric current was only generated when the magnetic field was changing, either when it was first being created or when it was collapsing. The key was motion. He quickly confirmed this principle with another, simpler experiment. He took a hollow coil of wire and connected it to his galvanometer. When he pushed a bar magnet into the coil, the needle jumped. When he held the magnet still inside the coil, the needle was still. When he pulled the magnet out, the needle jumped in the opposite direction. He had discovered electromagnetic induction. A changing magnetic field creates an electric current. This discovery was arguably the most significant of Faraday's entire career, and one of the most important in the history of science and technology. It was the principle that made the large-scale generation of electricity possible. Every power plant in the world, whether it's powered by coal, nuclear energy, wind, or water, uses this exact principle. A turbine spins a magnet inside a coil of wire, or a coil inside a magnetic field, and this motion generates the electricity that powers our homes, cities, and industries. Faraday had not just found a new scientific law, he had given humanity the key to the electrical age. He had turned motion into light and power. By the 1840s, Michael Faraday was already a scientific legend, but his questing mind was not done yet. He held a deep, almost mystical belief in the unity of nature's forces. He suspected that all the fundamental forces, electricity, magnetism, gravity and light, were somehow interconnected. He had already proven the profound link between electricity and magnetism. Now, he turned his attention to what seemed like an even more audacious goal, proving a connection between magnetism and light. At the time, this was a radical idea. Light was thought to be one thing, and magnetism a completely separate phenomenon. How could a magnet possibly affect a beam of light? Faraday spent years trying to design an experiment to test his hypothesis. He tried passing polarized light waves that vibrate in a single plane, through various substances while they were subjected to strong electrical fields, but he saw no effect. He was on the verge of giving up, but his persistence drove him to try one last time, this time using a magnetic field instead. For this experiment, he used a special piece of heavy lead-infused glass that he himself had developed years earlier for optical experiments. He placed this block of glass between the poles of a powerful electromagnet, the strongest one in the world at the time. He then passed a beam of polarized light through the glass, parallel to the direction of the magnetic field. With the electromagnet off, he used a second polarizing filter, an analyzer, to block the light completely, making the field of view dark. Then, he turned on the electromagnet. Instantly, light reappeared. The magnetic field had done something to the light beam as it passed through the glass. To Faraday, this was a moment of pure triumph. He found that the magnetic field had rotated the plane of polarization of the light. The stronger the magnet, the greater the rotation. He had found the connection he had been searching for. This phenomenon is now known as the Faraday Effect or magneto-optical effect. This discovery was the first experimental evidence that light and magnetism were related. It was a profound insight into the fundamental nature of reality. Faraday himself saw it as a crowning achievement, a confirmation of his belief in the unity of forces. He speculated that light itself might be a form of vibration traveling along the magnetic lines of force. While his specific interpretation wasn't quite right, his experimental result was the crucial clue that inspired the next great physicist, James Clerk Maxwell. Maxwell took Faraday's ideas about fields and his discovery of the Faraday effect and unified them into a set of elegant mathematical equations, proving that light is, in fact, an electromagnetic wave. Faraday had laid the final crucial piece of the experimental puzzle. Michael Faraday never forgot his own humble beginnings and the thrill he felt as a young man attending Sir Humphry Davy's lectures. He believed passionately that science was not just for academics in ivory towers but was for everyone. He felt a deep sense of duty to share the wonder and excitement of scientific discovery with the public, especially with young people. This commitment to education became one of the most beloved aspects of his career. He was not just a brilliant researcher, he was a gifted communicator who could make complex ideas understandable and exciting for any audience, using simple language and, most importantly, spectacular demonstrations. His most famous educational initiative began in 1825, when he founded the Royal Institution Christmas Lectures. The idea was to create a series of lectures on a single scientific topic, presented during the Christmas holidays specifically for a juvenile audience. Faraday himself delivered many of these lectures, and they became a London institution. He would fill the stage with astonishing experiments, making sparks fly, liquids change color, and gases explode. He talked to the children not as a lofty professor, but as a fellow enthusiast sharing his own sense of wonder. His most famous series, The Chemical History of a Candle, used a simple candle to explain combustion, capillary action, and the nature of matter in a way that was both entertaining and deeply educational. Faraday's talent for teaching extended beyond the lecture hall. He also wrote books aimed at guiding others in the practice of science. His 1827 book, Chemical Manipulation, was a detailed manual on laboratory techniques. It was a practical guide that taught aspiring scientists how to handle equipment, conduct experiments accurately, and observe phenomena carefully. It was in essence a distillation of the hands-on knowledge he had acquired over years of meticulous work. He was democratizing science, giving others the tools they needed to follow in his footsteps and make their own discoveries. He believed that the ability to experiment was a skill that could be taught and learned by anyone with enough patience and curiosity. This dedication to public outreach transformed the relationship between science and society. Before Faraday, science was often seen as a remote and inaccessible pursuit. He helped make it a vital and exciting part of public culture. The Christmas lectures continue to this day, broadcast on television and inspiring new generations of young people to take an interest in science and engineering. Faraday understood a fundamental truth: a discovery is only truly powerful when it is shared. His legacy as an educator is just as profound as his legacy as a scientist, proving that the greatest minds have a gift not only for finding the truth, but for sharing it with the world. Throughout his life of extraordinary achievement, Michael Faraday remained a man of profound humility and simple living. His actions were guided by a deep personal faith and a strong ethical code. He saw his scientific work not as a path to fame or fortune, but as a way of reading God's book of nature. This perspective gave him a remarkable detachment from the worldly honors that were frequently offered to him. He famously declined a knighthood, stating simply, "I must remain plain Michael Faraday to the last." He also twice refused the presidency of the prestigious Royal Society, believing such administrative roles would distract him from his true calling, scientific research. His personal life was marked by the same simplicity and integrity. He and his wife Sarah lived in a small apartment at the Royal Institution for most of their lives. He was not interested in accumulating wealth, and he even resigned from lucrative consulting work for industrial and government clients, so he could devote all his time to his pure research. In an age of intense scientific rivalries and disputes over priority, Faraday was known for his generosity and his focus on the work itself. His character was as admirable as his intellect, serving as a powerful example of a life dedicated wholly to the pursuit of knowledge for its own sake, free from ego and ambition. Faraday's influence on the world we live in today is almost impossible to overstate. His discovery of electromagnetic induction is the bedrock of our entire electrical infrastructure. The principles he uncovered are at work every time we turn on a light, use a computer, or start an electric car. The electric motor, born from his simple rotating wire experiment, powers countless aspects of modern life. His experimental work on lines of force provided the conceptual foundation for James Clerk Maxwell's unified theory of electromagnetism, one of the pillars of modern physics. He didn't just make discoveries, he gave us a new way to see the invisible forces that shape our universe. His legacy is permanently etched into the language of science itself. The farad, the unit of electrical capacitance, is named in his honor. The Faraday constant is a crucial value in electrochemistry. A Faraday cage is an enclosure that blocks electromagnetic fields, a principle he discovered and that is used today to protect sensitive electronic equipment. Michael Faraday passed away on August 25, 1867, but his work endures. He was the blacksmith's son who had little schooling but saw what no one else could see. He was the unsung genius who revealed the invisible forces that bind our world, and in doing so powered the future.